Good morning. I'm Suan Shin, PhD student in Seoul National University. First, I thank the Japanese Science Meeting Committee for giving me the chance to present our work. Today, I will talk about our research about the criterion function at reduced 5, improved by artificial neural network and Bayesian information criterion. Criterion luminosity function is criterion number density as a function of luminosity. Considering that the quasar mode is related to supermassive black holes, it could be crucial key to investigate the evolution of quasars and evolution of supermassive black hole and host galaxies. And it also can be used for estimating the contribution of quasars to maintaining the intergalactic medium ionized in the early universe. So many studies have been conducted for quasar surveys to construct the quasar luminous function at various redshifts. The quasar luminous function is often described by the power law functions. The faint and the slope is alpha, and the flat and the slope is beta. And as you can see in the vector graph, there are fewer data points in the faint part of the quasar luminous function and its fiber compared to its brighter part. Due to the shallow image depths of previous surveys, it is hard to find faint quasars. Therefore, it is very difficult to constrain the faint and the slope. Causing a huge discrepancy in the faint and slope from -1.2 and -2. To elevate the difference, the securing faint quasar sample is essential. So we want to extend the faint end of quasar luminous function average 5 as much as possible based on recent deep imaging surveys. Deep imaging data is one of two requirements to search faint quasars. The other is efficient selection method, which can distinguish promising quasar candidates from other contaminant sources. Since end of stars and high-order galaxies have similar colors to those of quasars, they could be contaminant sources. So to remove them, the conventional color selection is widely used for selecting high-order quasars. However, as you can see in the left graph, selections using 2 or 3 colors and maximums cannot properly distinguish quasars from few dwarf stars and almost all of the galaxies. They are indistinguishable in the two-dimensional color space. On the other hand, the NIDA 2020 derived recent quasar luminous function and what is the 5, without considering that the faint is the 2 beams due to possible contamination by lion-bird galaxies. This is because high-redshift galaxies become dominant population at the faint part of quasar luminous functions. So we have to make a new approach to select the quasars without contaminant source, especially for high-redshift galaxies. So we apply the deep learning and delta VAC calculation as our new and novel selection method. The reason why we suggest deep learning as our new method, it is known as great solver to classification problem, and it can determine the color criteria in multi-dimensional space, whereas color selections is determined by two-dimensional color space. And it also enables us to separate objects based on non-linear boundaries, and which can be optimized by training process. And furthermore, the computing time for deep learning selections is much shorter than acid fitting, and it is very useful to select rare objects in astronomical big data. And the Bayesian information criterion is a criterion to select the preferable model to observe the data. This criterion considers not only the likelihood and the number of data, but also the number of parameters. So as you know, the film widget becomes better as the number of model parameters increases. So if we want to compare the film result from models with different K, we should give a penalty to the model with a large K and calculate on Bayesian information criteria. The difference in Bayesian information criterion between models, the delta VIC indicate how much the observed data is close to a given model. So in our definition, if delta VIC is larger than 10, we consider a candidate as our promising quasar candidates. In our previous work, SNETR 2020, we performed acid fitting for quasar candidates using Dwarf and quasar acid models, and we calculated delta VIC values. And we found that the candidates with large delta VIC values are real quasars average to 5. So this suggests that it is efficient to discern quasar-like candidates. So based on deep learning and Bayesian information criterion, we searched for anti-quasars. To achieve this purpose, we use the catalog of HSCSSB PDL2, and these surveys comprise 3 layers depending on depth and area. We use a deep layer, which is observed with 2 narrow bands as well as 5 broad bands. And the survey area is 26 square degree, and the 5 sigma depth per point source in I band is 26.7 magnitude. Based on deep imaging data, we aim to make our quasar luminous functions 1 magnitude deeper than previously reported UV luminous functions. Before applying our deep learning and delta VIC calculations, we pre-selected our candidates, which have reliable photometry and appeared as point source selections. Since we focused on quasars, which outshine the host galaxies, it is very important criterion. Then we picked up weather object, which is the prominent feature of high-resolution quasars due to the intergalactic medium absorptions. Then we trained 4 layered neural network, accepting 6 colors as its input and providing the probability to be quasars or non-quasars as its output. It is worth noting that the non-quasars comprise non-detected point source. So using deep learning model, we aim to exclude non-quasar objects from pre-selected quasar candidates. And the performance of deep learning is shown in computer metrics. And as you can see, the true positive rate, the ratio of quasars classified as quasars by deep learning is close to 100%. And surprisingly, the first positive rate, which is related to contamination rate of our quasar survey by non-quasar subject, is as low as 0.5%. Although the first positive rate of deep learning is extremely low, it cannot account for a difference in actual numbers of non-quasars and quasars in the real world. So we adapted the delta VIC calculations as an additional step for removing this classified non-quasars object. And we performed acid fitting using quasar and star acid models and calculate the delta VIC values. So as a result, we exclude the considerable candidates with delta VIC values less than 10. And we visually inspected the HSA FSP images of VIC selected quasar candidates, and the visually inspected quasar candidates are expressed in black diamonds on this plot. And these candidates have a bimodal distribution in absolute magnitude, implying possible contamination by line-of-sight galaxy. So we consider quasars with brighter than -22 mag as our final quasar candidates. Based on our final quasar candidates, we built quasar luminous function of Reddish 5, reaching -22 mag without multi-wavelength data, which is 1 magnitude deeper than previous UV luminous functions. And we we derived the Benton slope of minus 1.6, which is constant with the previous surveys. And based on low number density of faint quasars, we conclude that quasars did not significantly contribute the ionizing background. And we also found a clear difference of the number density. The faint part of the quasar luminous functions between ours and the Rutherford galaxy are reduced to 5. This might imply the low contamination rate of private galaxies. Then we check the efficiency of our quasar selection process by estimating contamination and the recovery rate. First, we estimate the galaxy contaminations by applying our selection and color selections to spectroscopically confirmed lineup by galaxies. Among 8 galaxies, 3 galaxies satisfy the need of 2020 color collections, whereas our selections selected only 1 galaxy. Although this is based on small number statistic, it might imply our selection is more effective at separating quasars from lineup by galaxies. So to figure out the reason why our selection is more effective, we normalize the LCD of quasars and lineup by galaxy to their I-band fluxes, and we found that the quasars have more intrinsically ladder continuum than those of lineup by galaxies. This distinctive feature is cannot properly stanford by a selection using 2 or 3 colors at maximum. However, our selection using other colors can select this, can trace this feature. We estimated recovery rate of known quasars. In our survey area, there are 6 known quasars and 3 promising candidates. And unfortunately, the delta BIC calculation, this is 1 quasars and 1 candidate, giving the resulting in the risk rate of 22%. However, when we add the near infrared and medium band data, the delta BIC values can be increased from 5 to 50. So this emphasizes the importance of using multi-wavelength data. Then since we use the deep learning as an alternative selection method to color selection, so we want to compare the performance of deep learning to that of the color selection. So we calculate the confusion matrix for 2 methods. And as you can see, the deep learning has a very high true positive rate and extremely low false positive rate. However, color selections have very low true positive rate, which is close to 30%. This is because color selection is only effective for finding quasars at specific redshift range. So if we want to find quasars or rare quasars regardless of their redshifts, it is better to use deep learning than color selections to increase the chance to find quasars. Then this is our summary for our work, and I think we expect the combination of our efficient selection method and Gemini facility will have a great synergy on a distant quasar service. So thank you for your time.
Thank you, Suyan. And is there any questions to Suyan?
Hi, it was great talk. Can you comment a bit on the sensitivity of your BIC metric on imbalance in your training sample?
Could you repeat your questions?
If you could comment on the sensitivity of your delta BIC metric on the imbalance in your training sample.
Delta BIC? Are you asking about delta BIC selected candidates or?
No, I was just curious if how this delta Bayesian information criterion depended on the imbalance in your training sample? Like, how many-
Uh-huh.
yeah.
Uh-huh. First of all, yeah, great questions. As you mentioned, there are imbalance problem in the training sample. So we used quasar models, acid models averaged between 4.5 to 5.5 as our quasar training sample. Because there are few quasar, real quasars in our survey area.
Right. And how many contaminants did you have in your training sample?
So we use the same number of the samples in quasar class and non-quasar class, about 100,000 samples.
Awesome. Thank you.
Thank you.
Is there any questions from the audience or Slack? So now you have this optical imaging data. So do you have plan to apply for the Gemini spectroscopic follow-up?
Yeah, right. Definitely. I will have to. Yeah.
Thank you. Let's
Thank you.
thank again to Xian.